All right, so a topic that goes hand in hand with thermodynamics is equilibrium. So reactions, for the most part, aren't A turning into B. Most reactions are A in equilibrium with B, right? So some of A turns into B, some of B turns into A until it reaches some kind of point, right? And we can have stoichiometric values in here. And this double arrow is an equilibrium arrow. And so what this means at the end is you're going to have a mixture of A and B. Sometimes we'll still use this arrow to indicate that although there's a mixture of them, it's just grossly to one side, right? So it's technically still an equilibrium, but maybe B makes up like 99.999% of the components. And so we just draw a straight arrow. If we think back to Gen Chem, we have an equilibrium constant, that's K. And this is going to be equal to the ratio of products taken to their coefficients over the reactants taken to their coefficients, right? So in this case, it would be the concentration of B, which is our product, to whatever the coefficient is, 1, 2, 3, something like that, over A to whatever its coefficient is again. And so a question you might be asking is, why not all B, right? Why doesn't it all turn into B? Why does some of it stay as A? Well, it's kind of like the ball on the hill analogy, right? If you have a hill up here and a hill down here, your overall hill is going to look something like this, right? If these are your 2 points, you're going to have some kind of middle hill in between, and this is true for our G, right? And so if we take a look at this x-axis, what this is a ratio of products over reactants. And so we can see that neither fully all products or all reactants is going to be the lowest in energy. The lowest in energy is going to be somewhat of a mixture, but it's going to point towards whichever one is lower, right? So if on the left we have all reactants, and on the right we have all products, this right here would be our equilibrium, and it's going to go towards more product. And so this is your energy minima, otherwise known as K. Note that these kinds of diagrams are different than the reaction coordinate diagrams that we'll take a look on later, right? So they're not the same reaction. Here we have products over reactants as our x-axis, and here we have reaction coordinate as the x-axis. And of course, basically K and delta G are approximately the same thing. They're talking about the same thing. Delta G is equal to negative RT ln K, right? So there's a mathematical relationship between the two. And so when your delta G is very negative, so for example, maybe your delta G is negative 17 kilojoules, your K is going to be very large, right? Your delta G is negative, so it's favoring the forward progress. So you're going to have a lot of products, and K is products over reactants, so it'll be very big. So something like 10 to the third. And if you have 10 to the third, you probably have approximately 99.9% of products, right? And then as delta G gets closer to 0, you get an more even mixture. When it does equal to 0, K is equal to 1, and you have a 50-50 mixture of reactants and products, and then vice versa, right? So for example, delta G is positive 6 kilojoules. Now your K will be less than 1. So your K here could be 0.1. And approximately you're only going to have 10% of product. You don't really have to know too much of this stuff. It's just a little refresher and a background for why all of these reactions happen.